Hello, class. So we come to chapter 6, section 6.3, the binomial distribution. So as we hear in here is the word binomial. So bi is two, right? In I think in the Greek language, bi is mean two, right? So basically, we're gonna have two outcome for each trials. It's like a success or failure, something like that, right? Or tail, heads, something like that. Or yes or no, right? Yes, no, something like that, right? So basically, this decision will provide you something like that. Okay, we're gonna finding probability using the binomial models in this session. Okay, so we moving to the next slide. Binomial probability models is useful for many situations with discrete numerical variables. Keep in mind that discrete is discrete numerical variable is variables that have like a whole numbers such as like 1, 2, 3, 4, 5, something like that. So right. You don't want to include some like decimal numbers in there, and there's no measurement in here at all, right? So we are looking for a fixed number of trials, which is n's usually, right? So like how many trials you're gonna try when you flip a coin, something like that, like 10 times or 10 trials, n is 10. Okay, so what else? We're gonna have to have two outcome possible at each trial. So like I say, yes or no, head or tails, success or failure, something like that, right? Number 3, we're gonna have the probability of success. So we notate as P, okay, small p is probability of success for each trial. So that mean what? That mean the probability of failure will be equal to what? 1 minus small p, right? Because by the complement way. So you're gonna do 1, you minus for the probability of success, which is a p. You're gonna get the probability of failure. So the trials are independent. So each trials independent to all the other one. Okay, so that is four things that you need to have for binomial probability model. Now let's take a look at the tossing a coin. So if you think about tossing a coin, you're going to have what? Head or tail, right? So these are two outcomes for each trials, right? Right. So that's we suppose you toss a coin 8 times. So how many trials you have? N equal to 8, right? And count the number of head. So we are interested in the head, right? So explain why this is an example of binomial experiment. So let's think about 4 things that we are looking for. First, there are a fixed number of trials. Yes, it was n equal to 8, right? What else? Each trial has only 2 outcomes, heads or tail. Yes, it's correct, right? And the probability of a landing on hand is the same of each child, right? So the first one you have probability to be half is a half, right? The second child also probability is a half. So every child must have the same probability as 1/2. Okay. Then number 4, trials are independent. So outcome of one toss do not affect the outcome of any other toss, right? So these all certified, and that's the reason why we say the tossing a coin is a binomial experiment. Okay, so now we're gonna consider about binomial or not binomial. So for each of following situations, identify which are binomials, and for the one that not binomial, explain why it's not binomial. Okay, so now you can go ahead and pause my videos and think about this case. Which one is binomial and which one is not, right? And after that, you can go back to check with the answer with me, right? Okay, so now we come back with the answer. So 1, record the age of a group of 20 randomly selected statistic students. So what are you doing? You record the age, right, of the group of 20 random selected students. How many outcomes can be? It could be like 18, right? It could be 19, 20, 21, 23, something like that, right? How many outcomes? Totally, it's very various, right? So I hope not gonna say one is a binomial distribution. Okay. So say no, because a child has more than 2 outcomes. I will say that, right? But let's see later. Let's check with our latest answer key. All right, number 2. Ask each partner of a married couple whether or not they exercise regularly. Okay, so this case have how many outcomes for each? Say whether or not they exercise regularly. So it's gonna be like yes, they exercise, or no, they're not, right? Right. So it's look like, oh wow, could be a binomial distribution here, but we have 4 things to check. Okay. We need the fixed int trials, right? We need what else? We need 2 outcome. Okay, it's 2 outcome already. We need the probability of landing. We need the probability must be the same. Is that the probability going to be the same? Right? Okay, maybe the next one. The trials are independent. Right? So, because the word married couple here, right? I would say not, right? I would say no, because it was married couple, so it just depend on each other. Okay, so because they are husband and wife and wife, so they are not independent. So really watch out with the case when you talk about like a married couple, right? Because you ask each partner, right? So usually in the husband go, then the wife also will, or something like that, right? Okay. Now the last the last problem say ask a random sample of workers whether their annual salary is greater than 50,000, right? So when you ask someone about, hey, are you is the annual salary is greater than 50,000, you're gonna say what? Yes or no, right? The quick answer gonna be yes or no, which means two outcome, right? Okay, so that is look good. um you can you can you can also have independent um independent for it independent property for each trial. Um so so this I would say yes. Okay. So now let's take a look at the answer that finalized, right? So first one is not by more binomial because each child do not have only two possible outcomes. The second one, not binomial, since the couple is married, the trials are not independent. Okay. The last one is binomial, not binomial. Okay. So Um, so now we have some ideas about binomials or not binomial already, right? So let's we move to the next slide. Oh, okay, now we learn about the shape of binomial distribution. Okay. So the shape of binomial distribution is actually depend on the number of trials and the probability of success, right? Probability of success. Yeah. So for examples, if I have probability of success is 0.3, like 30%, and I have like 15 trials to do this. So we're gonna have like a mm, uh, like a graph of the probability with the number of success down here, and the shape going to be look like school to the right, right? Because you can see that mostly is like for example it's like 4 6 4 5 and 6 2 4 5 and 6 up to there, right? It's the number of success is stay there for the probability. So for the one after that, it's gonna be like very less. So So how can we have like a symmetric? So think about when p equal to 0.5 and with the n is large, even if p is close to 0 or 1, it's still going to be symmetric. So there's two cases. The first case is when p equals to 0.5, you have symmetric, right? Right. The second case is I don't really care about p, but I use the n is pretty large, like hundreds, and then I still gonna have a symmetric. Okay. So now we're gonna move to the next slide. We're finding the binomial distribution. Oh, sorry, binomial probability. So binomial probability can be found by hand with using the binomial formula. So binomial formulas later I gotta show you. If n and x are relatively small, right? So I mean by hand, yeah, if like the number of trials and like how many success you want to have is small, then you could do by hand. Okay. Sometimes instead of like a small number is like a big number, then I don't think do by hand gonna be a good idea. So most application we're gonna do a technology that has binomial distribution built in is used to find binomial probability. Okay, so let's take a look at it. So for examples, let's finding binomial probability for one value of x. So according to the recent poll, 47% of Americans say it is important to control gun ownership. In a random sample of 200 Americans, find the probability that exactly 90 Americans say it is important to control gun ownership. So what the question about? Probability that exact 90 Americans say it is important to control gun ownership. So you are interested in the case that people say it is important to control gun ownership, right? So what the probability of people say yes, it is important to control gun ownership. So come back with the given there. It's say like 47%. So that is a probability of success, right? Which is 47% and equal to 0.47, right? So because we are interested in the people who say it is important to control gun ownership, so we can know that the percentage there is going to be the probability of success. Okay. What else do I have? I have in a random sample of 200 Americans. So that means you want to ask 200 people, right? Like 200 trials that you want to do to check yes or no, something like that, right? So I would say p, small p equal to 0.47 here, and equal to 200 here, right? What else? We want to have exactly 90 Americans, right? 90 people say yes, right? So I have X will be equal to 90. I want 90 people say yes. Okay. So let's we move to the next line and see what I do. Okay. First, I have to check if this is binomial problems, right? Because if it's not binomial, well, I don't wanna using binomial way to go, binomial formula to do it. I don't want to do that, right? Okay, so first, the first property, is this a fixed number of trials? Yes, right? It's 200. Say number 2, is that 2 outcomes for each trials? When you ask, is this important to control gun ownership? Then you're gonna say yes or no. So 2 outcome, right? Yes. Number 3, probability of success would mean like probability of people who say yes, it is important, will be 0.47, right? And the trials are independent, yes, absolutely, because they are not coupled, they just independent random variables. So number 4 is good. Okay, next. In this problem, we are looking for the binomial probability where n equal to 200, probability of success is 0.47, and x is like exact 90 people say yes into 200 there. Okay, so we're gonna use, I actually should change this to be like a capital B better, you know. We're gonna use the B notation, stand for binomial distribution with a parenthesis n, they say binomial n comma p comma x to denote this probability distribution. Okay. So now, okay, so now we have because we have n in here is 200, right? 200. X in here is 90, which is big numbers, right? So I don't think that it's a good idea to use hand at all. So in this case, we're gonna use technology to handle that. And I would like to teach you to using StatGrant to handle to finding the binomial probabilities for this case. Okay, so let's go ahead and open the StatGrant. Okay, so go to the StatGrant. Okay, at this point, I hope everyone did know how to get in StatGrant, right? So in StatGrant, you're gonna click on Stat. No, not click. Just move the mouse there, and then it's right away show you the tab with the calculators there. So just move the mouse to there, and then zoom out to the binomial, right? Click on that. Okay, now you have what? Okay, you have a graph with n equal to 10. Okay, actually n is 200, right? What's the probability? Probability success is 0.4, right? Is that? Let me make sure. 0.47 and x equal to 90. Okay, so I have changed this. So you have changed this to be equal to, not inequities. Because right now we say exactly, right? Exactly. So you must make equal to 90. Something wrong. Let me check. Yeah, I did everything correctly. All right, so compute. Here we go. Because the answer is 0.0482156, right? So it's really awesome with StatCrunch that you just some click and get it. All right. So we move back to the slide and see that the probability to get 90 people who say yes, like exactly 90, right? Who say yes in 200 people. You do research. It's gonna be 0.048 when you round to 3 decimal place, right? So it's mean like almost about 5% to get exactly 90 people in 200 people you wanna do research. Okay, so let's move to the next slide. We're asking you about using TI-84 calculators. Let me show you by calculators. TI-80. I have TI-83s. Let's open this. So, where is this? Over here. Okay. So let me calculate this one, right? So I have to push second, click second, and then go to the DIST distribution, right? Where that's over here, all right? Click on this one, and then you go down to binom PDF, right? Don't choose binom CDF. Binom CDF is cumulative density. So right now we are looking for exactly. Then you have to do PDF. Okay. So enter that. Put out 200, 0.47, and then 90. Close that. So we have N, P, and X. Right? N, comma, P, and comma, X. Right? Enter that. You have exact number that you did in StatCrunch. Okay. TI-84 is a case that you don't have internet, and you can use this method to handle it, right? So let's move to the next line with finding the binomial distribution for more than one value of x. So according to BLS, the unemployment rate in Detroit in June 2014 was 10.2%. Okay, so here's people who say, no, I don't have work, I don't have job, something like that. If a random sample of 15 people, right? So now you ask 15 people living in Detroit as that time was taken, find the probability that 3 or fewer was unemployed. So now you want to know the you want to know the probability. You are interested in the unemployed people, right? So we have P success, because we are looking for the unemployed. So the P success will be 10.2%. So 10.2% is equal to what? 10.2 divided by 100 is gonna be 0.102. Okay, so P equal to 0.102, right? We have 15 people who living in Detroit that we're gonna ask. So n equal to 15, and we're gonna find the probability that's 3 or fewer was unemployed. So keep in mind that right now we ask for 3 or fewer, right? Which means X is not only equal to exactly 3. X can be less than or equal to 3, right? Do you agree with me? Because it's 3 or fewer. So I'm looking for the probability of X less than or equal to 3. All right, so now let's go ahead and do this. So first, we're gonna check to make sure if it is binomial, right? So we have how many trials? 15. Yes, that's correct. It's fixed. We have how many outcome? 2, because people want to say, are you employed? Yes or no only, right? And number 3 is probability of success. So 0.102. And the last gonna be independent because there's no couple here, so to be independent. Okay, so next we have n equal to 15, p equal to 0.102, and then x is 3 or fewer. So that means x less than or equal to 3. On that mean we have x can be only 4 cases here: 0, 1, 2, or 3. Keep in mind that you don't want to have 0.5 because it is like, how many people say yes, right? Discrete. So you're gonna say, you're not gonna say like half of people say yes, that, right? So we need to compute the case for like x equal to 0, x equal to 1, x equal to 2, x equal to 3, something like that, right? Right, probability for x equal to 0, adding with property of x equal to 1, adding with x equal to 2, x equal to 3. You're adding all of them together to get the probability of x less than or equal to 3. Right? So you can I would say this is going to be easier to use by calculators, absolutely, right? Or stack runs. So however, in stack range, you don't want to have to, you don't want to, you don't need to count each case here, right? For example, if I go back to stack range, over here, right? Have how many trials? 15, right? Have probability of success gonna be what? I forgot. 0.102. And probability of success, if you choose for the first case, no one say yes. So, right? So this could be the 0.199 something. But this is just for one case, right? So like 0.199 in 3 decimal place for the first case, right? So like adding with second case is when it's 1 here. Let's compute 0.339. Right? And then for the third case, when x equals exactly 2, when we 0.2697, I have to round the 9 to be 0. So setting 0.27, right? Plus 0.27. Plus, where's the last case gonna be 3 here? Compute 0.133. 0.133, and then add them together, right? Add all these together, and you get, you're gonna have to use calculator now. 0.199 add with 0.339 add with 0.27 add with the last k 0.133, and the answer gonna be 0.941. So you can go by this way, but I'm gonna say, it's kind of inconvenient and could be an error, right? Because of like each case in here I did round in 3 decimal place, right? And it could affect the final answer here. So StackRange can have the way to do, to make is cumulative. Okay. So instead of say x equal to exactly for each k here, I make it less than or equal to, right? Less than or equal to. This is notation of less than or equal to. Okay. So x less than or equal to 3, and I compute that, and I got 0.94 at 2 decimal place. And if you want to 2 decimal place, 0.941, that's fine. And it's gonna be similar with the answer that I have before. Okay. So so one time from StackRange can have right ways. The answer is set up, find each case in here. So this is this depends on the cumulative here, right? What about TI-83s? How can I do that? Okay, so second distribute, go to the binomial CDI. So for the binomial PDF is have like for each case exactly equal to, right? But for CDF, it's always gonna say up to. Okay, so this CDF is just binomial distribution up to. So this is up to 3. So you can do that. Okay, so you start with 15 as the n. You comma, what's the probability for the success? 0.102. And then you want the x up to what? 3, right? So you call that, and thus you get 0.941 as 3 decimal place. So that is a way we do by TI-83. Right, so I did explain you with cumulative probability cumulative density function, so CDF, right, in calculators, right? And so then I did explain to use Lagrange. I also explained you to use calculators. Okay. And yeah, and that's it. So because the binomial distribution probability distribution models the probability of discrete random variables, so we just we have to pay close attention to the language. So if I say more than 5, it means 6, 7, 8, right, and up to n, like how many child, right? So if I say 5 or more, then it means start from 5, 5, 6, 7, 8, n, right, and up to n. In inequalities notation, for more than 5, you can say x is greater than 5. For 5 or more, I'll write as x greater than or equal to 5. So this the second case is include the 5. Okay. Now we're gonna move to the next one. Say a difference between the normal and the binomial distribution. So we did not need to worry about these distinctions with normal probability because for continuous numericals variables, the probability of getting 5 or more is the same as the probability of getting more than 5. So keep in mind that in normal distribution, I don't have to worry about the case like 5 or more, or more than 5, because they actually the same, right? Because it's really, I mean, I'm gonna say like really close to each other, like 5. I'm gonna say 5, and the next is gonna be like 5.00000, something like that, small, like really close to each other. So I mean, who care about that? Just very small. So so we don't worry about the case when I talk about 5 or more than 5 in normal, but in binomial we care about that. Okay. All right, so let's practice with identifies the X values when is say more than 6, right? So more than 6, what does that mean? Oh, it's gonna be 7, 8, 9, and so on up to n, right? What about fewer than 5? It's gonna be what? 0, 1, 2, 3, 4, 5. You don't gonna count the -1 because we are talking about discrete, so we don't have negative in here. Okay. And at least 7. Oh, at least 7. What does that mean? Oh, wait, for the second K, fewer than 5, I don't include 5 in here, right? So it's just up to 4 only. Right. In notation of inequities, more than 6, only x greater than 6. More fewer than 5, x less than 5. At least 7, which is x at least, which mean 7 inclusive, right? 8, 9, and so on up to n. Right? So inequity, you're gonna say x greater than or equal to 7. Between 3 and 7 inclusive. Okay, watch out with this k. It's a between 3 and 7. What does that mean? Okay, so I includes 3, right? I have 4, I have 5, I have 6, and I also have 7 inclusive. So inequities is gonna be like x in between, right? Inclusive, so equal to in between 3 and 7 inclusive there, right? And the last case is 10 or more, which means you have 10, you have 11, you have 12, and up to n. And in equation notation is going to be x greater than or equal to 10 inclusive, right? So I'm going to move to the next slide. See the answer, right? Exactly what I did. Okay. Okay, so let's have some more examples. So according to the report, only 11% of Californians lack medical insurance. Okay, so some people in California doesn't have medical insurance, Medicare insurance. So after the passing of ACA, down from previous rate is 17%. Is suppose a sample of 80 California was taken. So you ask 80 people something, right? So I would say n is 80 right away. And then find the probability that more than 15 lack medical insurance. So what you are interested in, lack medical insurance, right? So that mean P in here, the P of success will be 11%. Okay, so because right now we have this probability success. We don't, this 17 here, it's just for, just telling you some information that give you a trap to get in there. But no, we don't need it because it's like a previous rate. Okay, we don't need it. Between okay, so we have n p there, n here, and say more than 15, which is x greater than 5, not inclusive. Greater than 15, I mean, not inclusive, right? So it's gonna be like x equal to 16, 17, 18, and up to 80, right? A lot of work. So, however, in StatCrunch, it's gonna be a piece of cake. How many trial do you have? 80 people, right? Probability of success is gonna be 11%, with 0.11, right? 0.11, right? What is what is x can be greater than 15, right? It's gonna be 0.0128. So yeah. For the between 10 and 20, it's inclusive. It's actually like in between. So when you draw the in between, it's always make the arrows, face to the left side. So it's mean like x greater than or equal to 10 and 20 is greater than or equal to x, meaning that. So it's go like that. You don't draw the other way, okay? So we have property of that, which is 10, 11, 12, 13, 14, up to 20, right? So we're gonna using stack run like this. Now, this one is in between. See the word between here, right? So you don't have dash K in here for you. You actually have to click on the between button here to change is in between 10 to 20 and it's compute. Okay, so for the binomial calculators in stack runs it must go with inclusive. Okay, it's just must to note that is inclusive. All right, inclusive between 10 and 20. So what about you say exclusive, right? What about in between? What about exclusive, right? For like property of 10 less than x and less than 20, like you don't include 10 and 20 in there. So keep in mind that this is discrete. This is discrete, right? So so that means what x can be equal to 11, 12, 13, and so on up to 18 and 19, and you don't include the 20 at all, right? Okay, so that means what? If you convert it in the inclusive way, it's actually going to be the same as property of like in between 11 to 19 inclusive. Okay, inclusive. All right. So for that case, you will actually gonna use 11 and 19 in here when you do compute by stack runs. Okay, so so this go back to the problem that we're working on. You're gonna have 0.384 or 0.38. That's okay to me with 2 decimal places. All right, gonna be the answer. So let's take a look at the way we do by stack runs. right? For the part A, right? Part B, right? So that's all about how to find the probability of binomial distributions. You will maybe have to think about the mean in this binomial distributions. So now let's talk about it. In the binomial distribution, we sometimes call expected values. Expected value. Which is the same as mean. With the same meaning as mean. Okay, like what you expect to have, you know. Uh, so so it can be taught as the number of success we expect. So you're gonna think the mean is like the number of success we expect if the experiment was repeated n times. And with all distribution is tell us where the distribution balance. So the formulas is gonna use as mean will be equal to n the number of trials multiplied by the probability of success. So for examples, if you suppose to toss 15 times and count the number of heads, find and interpret the mean of the probability distribution. So the mean will be 15 and then multiplied by n multiplied by the probability of success. So each trial will have the probability of success going to be 0.5 or 50%. So 15 times p will be 7.5. So we expect that I'm gonna have about like 7 and 8 heads in 15 toss. Okay. So okay. So for example, another examples about mean of binomial experiments. So the mean represent the balancing of the distribution. So this be in the center here, right? Mean was about 7, 8 here. Okay, what about standard deviations, right? So it's measure the spread of distributions, and the formula is gonna be standard deviation gonna be square root of n times p multiplied by 1 minus p. Keep in mind that 1 minus p is the probability of failure, right? So so we can this can help us to approximate a range of value we will expect, and a range of value we will find surprising in a binomial distribution. So let's do an example here. During his career, major league baseball player Buster Posey of the San Francisco Giants has a batting average of 0.309, I said 308. Okay, so this means that he gets a hit about 30.8%. Okay, so yeah, so that means this is gonna be the probability of he get a hit. If he banned for 80 times in a season, we would expect him to get how many hits, right? Would it be unusual if he got 120 hits. So first, we need to find the expect number, which is the mean. The mean equal to n times p, right? N is how many times he hit? 480. So n equal to 480. P is like the percent his success in one hit. So 30.8%. So 0.308. So what is that going to be? Use the calculators. We have 480 multiplied by 0.308. We got 147.84. 147.84. Okay, so what else? So that mean what? That mean he expect to get expect to get 147 or 148 hit, right? What else? Okay, so they say, would it be unusual if he got 120 hits? Right. So we need to have the standard deviation first. Standard deviation is square root of n times p times 1 minus p. Square root of n is 480, right? Multiplied by p is 0.308. And multiplied by 1 minus 0.308. What do I have? I'm gonna use calculator. Say square root 480 multiplied by 0.308 multiplied by parenthesis 1 minus 0.308. Close that parenthesis, close the parenthesis for the square root and enter. Have 10.1146. Oh, I write 115. 10.115. So now you can you can think about trying to find like trying to find the mean plus and minus the two standard deviation to find, you know, no, actually you can just find the z-score for 120 hits over here to check if it's gonna be like more than 2 or less than -2, and say if it is unusual or not. So let's take a look as the solution we're gonna have. Okay, so first expected values, here we go. Standard deviation, here we go. Okay, so so we want to have like an expect policies to get by adding and minus thing with, you know, one standard deviation. Okay, so that's also makes more sense with 68% if you're using the symmetrics empirical rule, right? So it's going to be in between 137.7 minus 157.9. Okay, so the second question say, is this 120 gonna be unusual? You wanna check if you wanna convert it in z-score, and the z-score, if you're using z-score, you have 120 minus 147.8 and divide by 10.1, you're gonna get negative 2.75. This clearly is over 2 standard deviation. Like, you know, it's less than 2 standard deviation. So that's gonna be unusual. Okay. Okay, so 6.1 question: which of the following numerical variable is decreased? So so this question is just review. So yeah, this number of passenger, right? So these are practice for use in this chapter, so you can go ahead and take a look at that. All right, so I'm gonna stop my my videos here. If you have question, please let me know. So we stop section 6.3 and stop chapter 6 here. Okay, see you in chapter 7.